A garden watering container has the shape of an inverted right cone. Inverted means upside down, with the vertex, so that's the sharp end of the cone, inserted into the ground. Water is poured at a constant rate into the open circular top of the cone. Select the graph which best shows the relationship between the depth of the water in the container H and the time t. So what we have is we've got inverted right cone, which means it's something like a cone, like that, with a sharp end going into the ground. So something like that. Right angle, a right cone means that the top of the cone is exactly above the center of the base. So that's my right angle cone, inverted. What happens if I put in water at a constant rate? The constant rate means that the same volume of water is coming in at the top, into the circular top of the cone. The same volume every second is filled in here. Now we can see that within a certain time that the area at the bottom, so the volume here for the same height is much less than the volume that, let's say, we have for the same height in here. So the volume there is much more than the volume there. So as I fill water from the top, the height of this thing will slow down, because if I have 10 millimeters or 10 milliliters of water at the start, it will quickly fill up, but the higher I go, the less volume 10 milliliters will cover in the same area. So what will happen here is the following. We will have a quick increase in height, and as I go up, the height will become slower and slower, the height will increase. Now if we look at the constant rate, and we look at how does depth change in terms of time, we look at the gradient of this line. And if we look at the gradient of this line, we can see it's not this, because the depth, the gradient here is 0, so this means that the depth doesn't change, and nothing is actually going in, so it cannot be this one. This is a constant rate. Now this is typical if we put something in that have the same diameter all the time. So if I was filling a flask that was a rectangular base or a circular base like a cylinder, as I fill it in, the height will change at the same rate, because the volume everywhere in every cross section will be exactly the same. So this will be for something like this. If we look at C, the depth, remember, look at the rate. So the steeper the gradient, the quicker the depth's changing. So now we have here the gradient at any point on this graph here, we can see that the gradient is increasing. So if the gradient is increasing at the end, it means that the depth is changing much quicker than at the start. So that will be the opposite of what's happening here. This gradient of D is undefined. We don't get a gradient. It means in no time, like in no time, the depth have just increased from 0 to a maximum. So this is also impossible. So it must be E. We can see that the gradient at the start, the gradient of the tangent to the line there, is steeper than the tangent there. So the longer I pour it in, the slower the depth change in terms of time, and therefore my answer will be E. Question 2. Which of the following function is an example of a graph that shows a constant rate of change? Now remember, constant, the rate of change is all about what is the gradient of my graph. Now a quadratic equation is a parabola. There's nothing constant about that. Cubic function looks like this, or can look like that. So it's definitely not a constant rate of change. Hyperbola looks like this, or like this, so it's not a hyperbola. Linear graph means that the gradient is the same everywhere, and of course the circle changes all the time, so my answer must be D. In question number 3, which of the following rates is an instantaneous rate of change? So instantaneous rate means that on that moment. So let's quickly look at what's the possibilities. The temperature changes over the day. So the temperature changes over the day, so it cannot be A because it is changing. It's not at the exact time of the day. 200 liters of water flow into the lake in the last 30 minutes. We don't know how much flowed in at that exact moment, so it cannot be B. The speed of a cyclist as they complete the first lap of the race. So he complete this. So as he goes, there's the track. As he goes past that point at that moment, what is the speed? So it can be C. Let's check. A walker travels 4 kilometers in 40 minutes. It's not. This happens over time, so it cannot be D. A weight loss of 12 kilograms in 6 months. I want to know what I'm losing at this moment. And I myself is losing nothing, so it cannot be E, it must be C. The last question I'm going to also take a little bit of time to explain because we'll cover quite a few things here. In number 4 they ask, which of the following denotes the gradient between 2 points? And we look at the limit and we have fx plus h minus fx. So I'm going to pause the video and quickly draw a graph and remind you what is this all about. So what we're going to do is, let's say I have a curve fx. Let's have a curve fx. This is my x-axis, this is my y-axis. My curve is there, and what I want to do is I want to know what is the rate of change between 2 points. Between 2 points, if I have my first point here, and I say this is at some point x, I can say my y value is, if I put x into this function, I will find my value here. So this value of y, so my y coordinate is fx. If I go a certain distance here away from x and I call that h, then this my new point will be x plus h. And to find what is my y value at this point, I have to substitute x plus h into my equation, which will then make my new equation, my y value is f, if I insert that value x plus h in there. Now, if I want to find the gradient between 2 points, I know that the gradient equals the change in y over the change in x. In other words, we have y2 minus y1 over x2 minus x1. In this case, y2 is fx plus h, x plus h, minus y1, and y1 is fx, divide by x2, x2 is x plus h, and x1 is x, so take away x. Now I'm going to stop there because that's between 2 points. They ask us here, which of the following denotes the gradient between 2 points? That is between 2 points, and this is the gradient. Now if I simplify this, we can see that we're not working with a limit, because the limit is where h strives to be 0. So when are we using the limit where h strives to be 0? You will remember that when we moved to first principle, at this point we said that we're going to get closer and closer, and what I want to find out is the instantaneous gradient, which means what's the gradient at a point. So this is the gradient at a point, that's the gradient between 2 points. And if I look at the gradient at a point, the instantaneous rate of change, then it is the gradient is where the limit where h, because we bring that closer and closer, it can't be 0 because we can't divide by 0, but we can say it's the limit where h strives to be 0 for fx plus h minus fx, and x plus h minus x is h. So this is what we have here. See, that thing and that thing is the same. So E is for instantaneous. The limit where h strives to infinity, we haven't done it yet. It means that this h carries on forever. It's off the screen. What will be the gradient for that? And the gradient for that will be infinity, because this line, this gradient, will just go up and up and up and up and up. So it will go into infinity. So it can't be this one. The derivative of fx is the gradient. Remember, this is the derivative from first principle. So B is also the same as E. And so is the limit where h strives to be 0. This thing and this thing is exactly the same thing. So this is also the instantaneous rate. So the only one remaining is the correct one, and I've already got you to that when we were there. That is fx plus h minus fx over h. So that was a bit of a tricky one. The last question is What is, let's have a look at the piecewise. Sorry about the and R. I'm not going to re-record this. If we look at the piecewise function, we say the limit where x approaches -1 of hx is what? Now, if I have a piecewise, you don't have to, but what I'm going to quickly do is I'm going to draw this graph. So it says x squared minus 3. So x squared usually sits like that. Minus 3 means it's going to come down, and it's going to look like that. And 2x, this is y equals x. 2x means it's going to be like that. So what they say is where x is less or equal to 1. So somewhere here, I'm not too sure where, I have this thing that it is around about here. X squared minus 3, where x is less than 1. So if x is less than 1, we are looking at this part, because that is the part. When x is greater than 1, we're looking at the straight line, which means then it's going to carry on into there. So this is how this graph looks like. This is for the green part, and this is for the red part. So what we say is if the limit does exist, it needs to, when I approach x, if that is -1, if this is -1, for the limit to exist, it needs to come, if I approach from the left-hand side, it needs to be the same value as approaching from the right-hand side. Otherwise, it means the graph looks like at x minus 1, it looks like that. It doesn't approach from the left and from the right to the same point. So let's go and have a look if this is happening. So when I approach x from the negative side, I'm going to use my red equation. So I'm going to say when h equals -1, and I'm going to put -1 in there. What does x approach? And it is then -1 square take away 3. And -1 square is +1, 1 take away 3 is -2. If I then approach, so this is approaching from the left-hand side. If I approach from the right-hand side, then I'm going to put x into that because that's the green graph. That's where x is greater than -1. So when h approach -1 from the right-hand side, then I'm going to substitute in there. 2 times -1 is -2. Since this value and this value is the same, if I approach from the left and from the right, it does exist. And what is that limit? That limit is -2, which means this is my answer.